All right, welcome everyone. Uh, Welcome to the October monthly meeting for San Diego Machine Learning. So the first presentation today is going to be this paper called Writing in the Margins, Better Inference Pattern for Long Context Retrieval. So obviously LLMs are in the news a lot and not going to exclusively do LLM related papers, but we do have one, and I think it's a fun, interesting paper this week. So this paper has to do with RAG, and in particular, a relatively common case where you have long context RAG. So I think of like, oh, you are Boeing and you have 80 million pages of manuals about like any one given airplane. So when somebody asks a question, you're going to do, whether it's a vector database or a combination of other search techniques, you're going to search for relevant chunks of text, and then the LLM is going to get that text um, inserted and then answer questions based on that. Well, one of the things that we've seen is, aside from the retrieval problems, just that when you have really, really long contexts, then the performance can suffer. And so this use case is really not meant for shorter, easier problems. It's really meant for when you have very long context. And so what they do is the text snippets, chunks, I don't know what the different names that they have, but the information that you're retrieving, um, they're creating short summaries. They're extracting relevant text from each of these summaries. And they further optimize this by only picking summaries that are judged to be relevant to the overall task at hand. So when they do this, they then take all of your chunks of text that you normally have, and they add these summaries, and then you have your main prompt, your main question. Um, so the intent is that by having the right information and having it well condensed and having it be really close in terms of like how far back, how many tokens back you have to look, you don't have to look that far back. So then you don't really have this lost in the middle phenomenon because it's actually like pretty recent, pretty close to where the prompt is. What makes this different is that any of us could just build this using like LangChain or something like that. And what you would end up doing is you'd be doing lots of passes over the text, writing all these summaries and sticking them in there, and it would be actually quite expensive. So what's really clever about this, the stuff that we'll get into about how this technique works, is that they created these summaries in a way that adds relatively very little computational overhead. One of the reasons why I picked this paper is because whether or not this very specific technique takes off, I think the trick they used to make this cheap is something that other people are going to iterate on. And we're going to see a lot of variations on this that maybe somebody would say like, well, that was the first thing, but there's an even better way in which you can use this trick to get better, whatever, summary extraction, better use of this. Um, so ultimately, in the end, yeah, what I described is they that this is a technique that involves the way KV caches are built. We'll talk about that, and then they save these summaries for later and stick everything together. Okay, so let's talk a little bit about LLM inference. I'm assuming people are familiar with transformers, with decoder style LLMs like Llama, ChatGPT, all of these guys. So um, the core thing that we're talking about here that gets more expensive is the attention calculation. There are feed forward calculations, MLP layers that are actually quite expensive, but they're just matrix multiplies. And so basically, you know, everything that NVIDIA knows how has gone into speeding up those matrix multiplies the best they can, and there's nothing you can really do to optimize it if you're using that vanilla architecture. But the attention calculation is expensive, and there are things that people do. So vanilla, these are autoregressive um, models that predict the next token. So if you say, like I was saying, you're an airplane manufacturer, and so you pull back 20 chunks of text, and each of them is 1,000 tokens long. Maybe Real chunks would be a little bigger than that, but just for round numbers. Okay. So now you've got 20,000 tokens worth of text that you've pulled from your database. And so you're going to have some, generally like some system level prompt instructions at the very beginning for the LLM. Maybe you have some like triple quotes or something. Then you've had your different chunks of text. And at the very end, you say like, uh, my what's a who's it is leaking a little bit of oil. What should I do? Or something like that, or whatever, right? Now, in theory, you could treat this model just autoregressively like the way it was built. And so you could pass in the first token, and then it'll predict what the second token is. And then you pass in the first two tokens, and then it'll predict what the third token is. But the reality is, you don't actually care what its prediction of the second and the third token are because you have 20,000 approximately tokens. That's the system prompt, all of your text, and then your actual main prompt. Okay. So because you don't care what those predictions are, there's nothing stopping you from passing all of those 20,000 odd tokens in at once. This is the same thing that's done during training. During training, if you guys are familiar, we use a technique called teacher forcing, where it doesn't matter what the model predicts the second token is. You're always going to pass in the real second token and ask it what the prediction for the third token is. If you didn't do that, what would happen is if the model predicted something bad for the second token, then it would quickly just spiral off into like complete noise, complete garbage, right? So especially early in training, it's really important that they use this teacher forcing technique. I think there's been a small number of papers that talk about what if you didn't use teacher forcing. But certainly later on, you need to do it. And it actually really speeds things up when you use teacher forcing because it means that whatever your context length is, you can fill up the whole thing. And again, you don't have to do this one token at a time thing. So we pass in our 20,000 odd tokens and we can calculate all of the queries, keys, the attention scores, and whatever on all of those. And we get our 20,001st token, the first response token. At that point, we then have to decode one token at a time. There's no real shortcut. Yes, there's some other things like speculative decoding and whatever, but like vanilla wise, there really is no shortcut. You have to go one token at a time. What this paper is going to talk about is how do we take advantage of what's happening during the pre-fill stage when we're calculating keys and values on all of those 20,000 tokens before we start doing the one at a time. The one at a time is the one at a time. That's not going to change. So let's take a step back and talk a little bit about what the attention calculation is. And so then we'll understand this technique called chunked prefill. Okay. In attention, we calculate queries, keys, and values for every token position. So if as I've shown here, we've got 16 tokens so far, 0 through 15, then basically while we're on the 15th token, it's going to calculate a query from that by taking our input, multiplying it by the query weight matrix, and we'll have a vector. And then it's going to take every one of our tokens, 0 through 15, it's going to multiply it by the key matrix, and it's going to generate a vector. That's the key for each one of those tokens. When we do a matrix multiply, when we do the dot product of those vectors, the query with each of those keys, then what we're going to get is a scalar value, just a simple real number, and we're going to end up normalizing them so that they all add up to 1. And we can treat those like probabilities. We're going to use that as weighted sums for the values. I'm mostly going to talk about just the keys here, but anytime I say key, basically the same thing is happening with the values, that you take the input, you multiply by a weight matrix, you get a vector out, okay? But just to simplify things, I'm just going to talk about the queries and keys, but just know that any place where we're doing something with key, we're really kind of doing the same thing with values. So this one query that we calculated for the 15th token is being used to multiply against all 16 of those keys. I think for most people that's fairly intuitive that at this point we have the token number 15 and we generate a query and then we're just doing dot products. And so wherever there's the most similarity between that query vector and a particular key vector, let's say it's key number 12, then that's going to get a really big score, and then all the other ones. And in a simple world, you might have one score that's pretty close to one, and all the other ones are close to zero. And then that's when we loosely say, token 15 is attending to token 12, paying attention to token 12, and is not really paying attention to anything else. So I think it's pretty obvious that if you sort of write this pattern down as a grid, and you show that basically here are my queries in rows, starting with the first one and the bottom is the last one, that the situation I've been talking about, the exact same vector for the query is being used to multiply with all of the keys. However, even if you do this in 15, 16 different steps, it is also true that when you multiply this weight matrix, which at inference time, it's fixed, it's not changing, by the input token, you're going to get the exact same key every time for any given input. So not only is the query vector for any given row in this matrix that I've written the same, but the key in every column is identical. So it's usually less obvious to people because the naive way you would do this, you're going to recalculate the key every time you get to the new token. So you're going to do it for the zeroth, the very first token, you're going to calculate the key here at the initial step, and then you're going to recalculate it 15 more times. But what I'm saying is, even if you do it the naive way, the actual result, the numbers you have in that vector are going to be identical every time. So whether you recalculate it or you don't do the extra effort of recalculating it, the end result is going to be that in every one of these columns, the key is identical. So that's the key thing sorry for no pun intended, but that's the important thing to understand about how are we going to optimize the performance of this, because we actually don't need to recalculate the keys and values. We can actually just save them off, we can cache them, and we can reuse them. The other thing is in autoregressive, you guys may have seen that there's this pattern where a query can only attend to the words that came before it. I say word token interchangeably just to be a little bit more informal. You cannot attend to things in the future. And so that's why, whatever, in the middle here, token number 7 for this query, you see that it has access to itself and keys 0 through 6, but it cannot see tokens 8 through 15. So even if you have them there, what we make sure we do is that we mask them out and that we zero out. We don't use any of the dot products in the yellow here. So this is like vanilla attention. So what I'm going to do now is I'm going to slightly modify this particular, the way this particular grid looks, okay? And all I'm going to do is break it up into 4 sections. So it is true that if I'm just recalculating the keys from scratch, no matter how many times I do it, I'll get the same numbers for every column. And then instead of doing all 16 queries at once, I could do 4 at a time. And what I'm going to wind up doing is 4 by 16 multiplies instead of 1 16 by 16 multiply. It's the exact same number of flops. Okay, I'm not saving anything on the amount of math. I'm just breaking it up into smaller steps. This does, however, mean though that I am reducing my memory. Now this is a relatively small example. It's 4 and 16, but doing a 4 by 16 matrix multiply is a lot smaller for the GPU than doing a 16 by 16. And you could imagine in the extreme, right? We now have these models with 128,000 length context with 1 million length context. If you had 128,000 tokens, you're not going to tell the GPU to do the 128,000 by 120,000 matrix multiply all at once. You're going to break it down into smaller chunks, okay? And so this is a very simple way to do that, where you say, I have some sort of fixed number of queries that I take at a time, and I'm going to do it in steps. Question? Maybe like memorization. That's going to come in 2 more slides. Yes. Actually memorizing, caching these values. So any questions on the fact that if we just do these 4 smaller matrix multiplies and concatenate the results, that we're getting the exact same answers as on the previous slide. All right. So now I'm going to do one more change to this process. So you'll notice that, especially in the earlier steps, we have a whole bunch of stuff on the right that's yellow that we're going to zero out. Do I really need to do a 4 by 16 matrix multiply and then throw away 3/4 of it? I don't really need to do that. I could just never multiply the part I'm planning to throw away anyway. So here in this next step, we've simplified things. And what I did is I removed the rectangular portions that were just all yellow. Now, in this case, we're only going up to 16, so the savings might not seem like that, that huge. But you can imagine that if you're actually going up into the thousands, then being able to have much smaller chunks here. So in fact, step 1 is going to be smaller and faster and use less memory than step 4. Okay. But the main question I have is, does anybody have any questions, any concerns that once again, if we stitch these together and we fill in zeros every place where we remove stuff, we are now going to get the exact same answer, the exact same numbers that we got on the very first slide that was vanilla attention. All right. And so then now the final last step is in step 1, we calculated 4 sets of keys. There's no need to calculate them again. We can memorize them and we can just reuse those keys in step 2. Yeah, question?
The question I have is, are the keys the individual words in the sentence?
The keys, so when we calculate attention, again, we take the words that have been turned into vectors and we multiply them by a weight matrix. So it's possible that the weight matrix in the extreme could be all zeros except for a 1 in one spot, where it's basically saying, I only care about this one particular number, even though your word is like 4,096 floats. This one vector tells me if it's a noun. This one float tells me if it's a noun. And so I'm going to use that because what I want for this particular attention pattern is to match up with nouns. Okay, so we don't always know what the pattern is that they're looking for, but generally speaking, the keys that we talk about are sort of much smaller, semantically much narrower in meaning. In real LLMs, I'm not talking about it here. You have positional encoding, and there are certain operations where the key actually totally just focuses on the position. And it says basically, I'm going to, no matter what happens, you are going to attend to the token that was 2 before your current position. And so it's really actually completely ignoring the meaning of the word, and it's just focusing on where can I see that the positional embedding says that it's 2 less than where you are.
It's hard to understand how the model came to these conclusions.
What's hard is that in actuality, oftentimes there's multiple patterns all being superimposed in one calculation, and then things get merged later. So it's possible that this thing that's looking for nouns in a different context is looking for verbs, and a different context is looking for whatever, male things versus female things. And just depending on the situation, it's doing different things, right? So when the current word is a verb, it's looking for a prior noun. It's looking for the subject of the sentence. But when the current word is, something else, a preposition, then it's doing something completely different. So that's what makes it really hard, is that they're not just single use. But so again, so these are the vectors that are being converted, extracted. I don't know exactly what the right verb is, from the input tokens. Okay. Again, for whatever property that they're trying to match up the current word where the query is with a prior word. So a very common example is when you have pronouns. So if the current word is she, then one of the things the language model needs to do is it needs to know what earlier thing you talked about is she referring to. Okay, so that's a very clear example where you must have some kind of attention pattern that says, oh, earlier on, I actually said, Julie. So she refers to Julie. Okay. So yes, so once we've calculated the keys and values for the first 4 positions, when we do step 2 and we're doing the 8 of them, I could once again do the weight multiply against our input tokens, and I could recalculate them from scratch. But it's actually faster to just say, I memorize them, I cache them, and I'm going to reuse them. So the light blue is ones that we're reusing. This has some benefits in this 1, 2, 3, 4 step calculation, but it's actually not a huge benefit. The main reason why we do this caching, this memorization, is because when we get to the decoding phase, we're going to do one token at a time. And that makes very poor use of your GPU. You have this GPU that's like, I can multiply 1,000 by 1,000 matrices in less than a millisecond. And you're like, yeah, but I have one query. I only have one new query. Okay. Um, and so at that point, you're really much better off instead of saying, for long context, I'm going to calculate 100,000 keys and then have you dot them with all of them. And it's just like, oh, I'm just going to do a memory read and here's all your 100,000 keys. Now calculate one query and do the multiply. So, so the real purpose for this cache is for the decoding phase, not for now. But nevertheless, it is beneficial and we're going to build this cache anyway, so we might as well use it. Okay. So this pattern is what is called chunk prefill. Okay. Where you take, well, I was saying we have 20,000 tokens, right? It was 20 documents and plus some prompt and whatever. We are not going to, even if we had a big enough GPU that we could do it, we're not going to actually throw all 20,000 of them into the GPU at once. We're going to break it up to chunks. I actually don't do server inference stuff for a living, so I don't really know what's the real size. Is it 1,000? Is it a few thousand? You know, I'm not really sure, but it's something along those lines to do a slightly more manageable chunk. All right. Any questions about chunked prefill? Yeah.
But is that based on like you know are you adding that context at every step of LLM inference, or is it like a separate training movement?
So the questions about the weight vectors. So you mean the ones where to actually build your key query vector and your key vector? Yeah,
Yes.
yeah. So those are part of the LLM model. When you're training the LLM, uh, the primary thing you're doing is actually training those weight matrices. The attention calculation at that point is hard coded. It says that whatever query vector is, you're gonna dot it with the key, and you're going to use softmax to weight them so that they all sum to one. There's actually no learning happening in that part. It's all about, is the key going to pick out things for their nounness, for their big smallness, for a particular color, for odd evenness, whatever kinds of properties it's picking out, and then it's all the combinations of the different patterns of when the current word is blah, then this attention head will pay attention to the preceding noun. That attention head is going to pay attention to adjectives that might describe the current word. This other attention head is going to describe whatever. This one's going to memorize sort of the topic of the previous sentence. It doesn't really have anything to do with the current word, but it might be necessary to understand the current sentence. So it's all those patterns coming together that ultimately let you make sense of what is this text that I'm reading.
That's the basic.
Yep, exactly. So right now we're talking about inference. So we're saying this is a frozen, fully trained model. We just have millions of users that are trying to use our LLM and ask it questions. And so at this point, the query and the key weight matrices that build these vectors, they're frozen, they're fixed. We just want to do a lot of these matrix multiplies to actually serve as many users as we want. All right. So that was just a little bit of a background thing on chunked prefill. So in the paper they talk about, yeah, so your inference, you've got these two phases we talked about, the prefill and the decoding. And if you do this naively, you're going to do L, if you have a text length L, you're going to do L by L, so order L squared memory. One of the things that happens though is imagine I have some number of users. It could be one, but it could be I have a batch of like 4 users or whatever. If I have a long L and I put in 20,000 tokens, let's say I do have a batch of 8 users. Well, I'm waiting until all 20,000 of those finish their matrix multiplies before I get the results back for any of my 8 users. And not only that, the other users who are waiting for the GPU, they're all just sitting around waiting. Okay. So if you have a mix of short and long text from different users, you're actually much better off saying, I'm going to do this in chunks, and then the chunks can sort of all be fairly filled up because if I had 7 really short things where someone's just like, what's the capital of France? And then the answer is, Paris. Um, After I finish the first chunk in step 1 on the previous diagram, I can put a new user in my next batch of 8 along with the second chunk. And I can keep adding new users if they're all small in the next chunks. But if I just do one big giant batch, I'm waiting until that giant batch finishes. Um, so for both of those reasons, reducing the memory pressure and also allowing you sort of more checkpoints where you can decide like, who else I'm going to bundle with this work. Okay. So that's why uh, um, chunk prefill, it helps with both your memory, and then we're not really going to get into it, but it helps you combine users more efficiently into the operations that you're doing on your GPU. Okay, so now that we understand that portion, which they do talk about in the paper right at the beginning of the method section, now we got to talk about what specifically are they doing in writing in the margins. So we're going to assume we have a very long snippet of text and that our prompt is short. If that's not true, then you may not want to use this technique. Okay, if for some reason this would be extremely odd, if your prompt describing what you want the LLM to do is 10,000 tokens, and the text that you retrieve from the database is 1,000 tokens, then this is not a match, okay? But the common case is what they're talking about, where your prompt is whatever, dozens, couple hundred, tokens, something like that. So during this trunk prefill, what we're going to do is we're going to calculate the keys and values. But after each chunk, what I showed on the slide as step 1, 2, 3, 4, after each step, instead of immediately moving on to the next step, I'm actually going to ask the LLM to extract information from the text that it's seen so far. Okay. We'll get into on the next slides, how exactly do we do that? Okay. They also ask the LLM to rate the text that they're pulling out to give it the ability to say, well, you told me to extract text, but actually there's nothing. So instead of forcing it to give a summary, it also can just sort of say, nope, there's nothing yet. You wanted to know who was the first president of the United States. I don't see anything about presidents yet. It's just a whole bunch of stuff about the Constitution. So no. Um, and then finally, after they finish all of the chunk prefill and you're about to start the decoding phase, instead of just doing the prompt right then and there, they insert this summarized text that they've extracted there right before the prompt, and then they let the decoding happen as usual. So again, for my example about the 20,000 tokens, the 20 documents, about the airplane or whatever. So you could say system prompt, blah, 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 20 chunks, and then there would be just maybe dozens, maybe a couple, maybe 100 tokens or whatever that says like, I found this sentence that says, when tightening the bloody bloody blah, make sure never to apply more than 20 foot-pounds. And I found this chunk that says blah 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 can cause leaks. And I said blah blah blah, a crack here can cause leaks and da 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 da. And then now you have your prompt that says, hey, I'm leaking some fluid. What could be the cause? So hopefully then like that text is like right immediately before the question, what could be causing these leaks? And so instead of this huge problem of finding answers out of the 20,000, I have repeated, summarized, hopefully the best nuggets just right then and there. All right, whoops, 2 slides. So we have a visual diagram that explains this a little bit better. So this is standard RAG, okay? I don't really know. This is from the paper, so this is a different example, but their question, their main prompt is from some story or whatever, is Ethan Washington in a marble floored room? So what they're going to do is they're going to pull chunks of text from the novel, okay? And then we're going to do chunked prefill on this. And so this is each blue box represents one chunk. Again, I don't know what the actual real size is. Let's just say it's 4,000 tokens or whatever. We're going to do 4,000 tokens. And in vanilla rag, again, all you do is you just append these chunks and then you append your question. So you've got all these blue chunks, and then you have the question, is Ethan Washington in a marble floored room? And you just do decoding. And LLMs do a pretty good job, but we're talking about can we make it a little better? So the delta, we're going to take this, we're going to modify it. So now writing in the margins, after we've processed each blue chunk, we're going to tell it, hey, I want you to extract information relevant to the question, is Ethan Washington in a marble floored room? So if this text talks about Ethan Washington's childhood, whatever, it's talking about Ethan Washington's favorite foods, his taste in clothes, then it's just going to say, no, I don't have any text for you. But as soon as it sees a chunk that says something about where he lives and what the room looks like, whatever, whatever, then hopefully you're going to get this green text on the right that says, I found this text that says John's living room is marble floored. And then maybe something else that says Ethan Washington is in John's living room. And if you put those two things together, then yes, it is marble floored, right? So we're going to take these things, and we've got green and red ones. So then after we finished our regular chunked prefill with the blue, in, before we insert the question, is Ethan Washington, blah, 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 we're going to insert only the green chunks. So we're going to insert John's living room is marble floored, and we're going to insert Ethan Washington is in John's living room. Uh, in this case, we got a lucky ordering of those two, whatever, but and then the question. So you can see the real difference between regular rag and writing in the margins is just this one little green concatenation of margin summaries that appears before you get to your main question. So we haven't said anything about how the exact details, how they do this. But any questions so far, just in terms of what their goal is to create this special little green box of super summary info right before the question? Yeah. So the question is, what's the additional overhead? So let's talk about the actual technique so we can see what this overhead is. Okay. So we got to generate these summaries. How are we doing that? Okay. So after each chunk, when you're doing this chunk prefill, the chunk goes in and you calculate all the keys and values and you're planning to cache them. And normally what you're going to do then is you're going to throw everything away. You're going to clear memory. You're going to load the next chunk and you're going to do chunk prefill, right? Instead of doing that, what they do is they add a small prompt that says, hey, summarize, tell me if you've seen any text that has anything to do with, is Ethan Washington in a marble floored room? And if so, then they're going to do decoding, and the model is going to say, well, actually, I found this sentence that says John's living room is marble floored. It's not exactly Ethan, but it seems kind of relevant. And so then we'll take that text, not the floating point vectors or anything, just the text. And we'll say, yeah, I'm going to save that off. That's one of my green ones. Okay. So the summarization prompt we'll see in a couple slides. It's pretty short. It's a few dozen tokens. So it's not too expensive to compute. You are still doing query attention with everything that came before in the context text. So it's not like crazy cheap, but it's relatively cheap, and they're expecting the answer, what text have you seen that's related to this question? They're expecting the answer to be dozens of tokens. So it's a really short decoding phase. It's not like write me a chapter that's 5,000 words long, you know. Um, so I don't have numbers, but the gist is it's relatively inexpensive. So then what they do down here is they save off the text, and then the LLM, it originally did this chunked prefill, and now we've done extra work where we had the special prompt that says, "Give me a summary." Have you seen anything related to the marble floored? Blah, 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 blah. And we just throw all of that away. So we're building this KV cache, and we make sure we do not include that in the KV cache. We're just completely throwing that away. Okay. And so from the perspective of the KV cache, it's as if you never did that special decoding question of summarize what you've seen from the text so far. It's completely oblivious that this ever happened. Yes, you actually did take over whatever operations for a little while and you calculated that. But since you threw it away, it knows nothing. And so you have to do a little bit of bookkeeping. You have to make sure that, like, for example, if you're on token 5,000, you add this little question in there and it generates the summary. So technically it's at like token now like 5,090, right? You need to make sure that when you go to do the next chunk of chunk prefill that you rewind everything back to say you're at 5,000 again, as if it never happened. But as long as you do that bookkeeping, the KV cache chunk prefill has no idea that any of this stuff ever got snuck in. In addition to the summary generation, they also asked to classify, and they mentioned that you could do this as a separate task. In the paper, they just combine it. So what they actually say is, tell me yes or no, did you find any text? And if the answer is yes, then show me the text. Okay, and so here's the actual prompt on the right. And so what they're really saying is um, 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 copy over all context relevant to the question is whatever his name living in a marble floored room. Okay. So they are always repeat any place where you see query, they're repeating, they're pasting in the main question. And I think this is one of the things that makes this technique better than other things that people have done, because you can generically ask the LLM to summarize each chunk that it sees, but it doesn't know with respect to what. If it's the airplane thing, are you summarizing it with respect to how to build an airplane? Are you summarizing it with respect to how to take it apart and junk it for parts? Or are you trying to summarize it with respect to I'm leaking oil? So because they paste in and they say, I want information relevant to blah, 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 the main question, now your summaries can be much more targeted. And I know that, oh, you care about leaking oil, and therefore um, I can do a much, much better job picking out just the parts that you need to know. So this is not something that you could just pre-calculate and put in your vector database, because you need to know what the question is. For each different question, you're going to get different margin notes. So again, this process is relatively fast. You can see this is not a crazy short prompt. I don't know what this is, 100 odd tokens. Um, but once again, this is why we said the use case is assuming that you have very large context. So if our context is 100,000 tokens, that makes this extra work more negligible in comparison. If we had a very short context and it was just like one paragraph chunks and we had 6 of them, then the cost of answering this question compared to that is comparable. And so then you're maybe doubling, tripling the cost of doing RAG by inserting this. So again, you need to like kind of decide when it's appropriate. It from what I've seen, it is relatively common that you have very large text coming back. Even if the snippets are shorter, what people often do is they crank up the number of hits that they're returning to try to maximize as much as they can pull back. So even if you did have shorter ones, you're like, well, I don't want 20 then. I want 40, because I know that sometimes retrieval doesn't get the right thing in the top 20, but my odds are going to be higher if I do top 40. So generally speaking, I think the long context is a very, very common case. So it is quite applicable. All right. And then here we just see the modified main prompt. So I said they insert the green snippets, the green extracted text here. They actually have a little bit more around it. So they have some text that says things like, I asked my assistant to read and analyze the above context. So this is the 20,000 token documents that you pulled from your database. Analyze the above content page by page to help you complete this task. Those are margin notes left on each page, or those are margin notes left on each page, and then boom, 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 all of your green ones. Okay. Uh, and then finally, they say, read again these notes and the original provided context, the 20 long documents. Take a deep breath and answer the question. And then the original question was John so and so in a marble floored room. Okay. So there's a little bit of work here, a little prompt engineering, going into like figuring this out. But they are explaining like they don't just like slam the text in there. They're sort of explaining like how this text is different from the main chunks. They're like, my assistant wrote these helpful margin notes. Um, and we'll see that there's an ablation that they did where it's like, well, what if maybe you don't need the text anymore? Maybe I just use the margin notes instead, and da da da. So we'll see that in a second. But so basically, this is the technique then. So there's the special extraction technique on the previous slide, which again, it's not super cheap, but it's using the fact that your KV cache is already loaded up and ready to go. Okay. And then there's this. So we'll talk a little bit about some of the results that they had. Any questions just on the technique? So again, the really clever part is this idea that I've got the KV cache. Not only is it pre-calculated, but it's literally like on the GPU. I just calculated. It's right there. So it's very little work for me, not just in terms of calculating keys and values, but even in terms of memory copying. Yeah, Christian. Uh, so the question is the caching, can it be done like at the Python level or like C or whatever? I I don't really know exactly how people implement this stuff, but basically it's at a level a little lower than just like if you're building a neural network in PyTorch and Python or whatever, right? So it's really like uh, uh, looking at the sub steps that are happening um, on the GPU and in what order. So I would expect that it's generally speaking like CUDA code, and I'm assuming that stuff's mostly written in C. So um, they did actually, there is a repo, there is a library, and it's on Hugging Face. So you can actually try this. You don't have to write your own. They wrote it already. And so you could actually try writing in the margins on an example and see if it does better than Vanilla Rag. Yep. Yeah.
Chunks that calculating content uh, chunks. Um, was there any mention of like all? Because I'm thinking like maybe like looking at the order could account for like what's it called, like loss and fill bias or other sort of stuff like that. Do they or do you think that like it seems like these are like all modular now, like flipping out the context, put that cache instead.
Yeah, so briefly to summarize, the question in the room was about like the order of processing things and whether that might help with sort of lost in the middle. Um, I don't think uh, I don't think off the top of my head there's a really easy solution for that. So the main length of my long context is all the stuff that I pulled out from the database. I suppose you could try to order those because you do have them ranked presumably by which was the closest hit and which was the least. So you might say want the closest hit to be last, closest to the question, not first, not the oldest, farthest away thing, right? But the middle's still going to be the middle no matter how you order them, and there's no not to me at least no obvious way you can sort of get around that problem. Obviously, if you somehow had hierarchical, if you had some other information, then maybe, you could. But at least my very light familiarity with vanilla RAG is that the documents you come back are generally all treated equal. There's no, other than the fact that some are closer matches than others, but there's no like, oh, well, this is a really good document because this comes from the instruction manual, and this is a really crappy document because it came from a blog post or something like that. Generally, if you put it in your database, you thought it was reasonable, and so then it just pulls back everything it can. All right. So they did some evaluation, and there's three tasks. So multi-hop question answering. The example from the paper, he's in John's living room, and John's living room has a marble floor. That would be two hops. Okay. One hop would just be this dude lives in a marble floored house. Okay. And so that's a much easier problem. So multi-hop is harder, and we have two benchmarks for that. There's this needle retrieval single hop, so squad is much easier. And then there's this aggregation task that I'm not super familiar with, common words extraction. So imagine that you're given texts that's 64,000 words, and all these random words appear there, and some words appear no more than 50 times, but a handful of words appear at least 500 times. After reading this text, can you tell me which are the words that appeared a lot, at least 500 times? So what are the common words versus the rare words? And so that's kind of an interesting question, which, like if you're just in a programming language and you just like write a for loop, like you can do, right? But transformers, you know, they can't do for loops. And so it's kind of an interesting problem for them. And so in brief, they said, hey, our model did well. It didn't actually do so great on squad. And presumably it's because the one hop task was too easy. So regular vanilla RAG was able to do just fine on one hop because if the text actually says somewhere, the dude lives in a marble floored living room and that gets pulled out, then attention can just sort of find that text even out of 100,000 tokens just fine. What was kind of interesting to me though was it wasn't that RAG was faster and did just fine, but it actually did better. So somehow writing in the margins with this extra stuff slightly lowered their scores relative to just vanilla RAG. But then they said, hey, we did well on these other problems. For some of them, it was much more noticeable as it got bigger. So for 16K of text in there, the LLM can do a much better job finding stuff. But when you get to like 64K of text, it's harder to find stuff randomly from the middle somewhere. And so high level, that's kind of how I would summarize their results. Briefly, they also have two ablations they did. So the one on the left is, as we said, there was the red and the green summaries. So what if they didn't do the red and the green business and they just said, hey, always take all of them and concatenate them and stick them in there. And at first, when I read the paper, I was like, oh, I think, I wouldn't have expected there to be that much difference between the two. I don't really feel like filtering is going to do that much for you. But then after I thought about it a little bit more, I realized that my initial mental model for the paper is you get 20 things back from your database and you do a summary of each one of those 20 things. Some of them may not be as relevant, but whatever. But that was the wrong mental model. Chunked prefill is every, 4,000 tokens. And so sometimes it might only be half of one of the documents that came back. Sometimes it might be two different documents smushed together. And it's not going to end cleanly at the boundary between documents that you pull back. It's just going to be every 4,000 tokens, it's doing a chunk. So especially the very early chunks, if you have long things that you're pulling, big things you're pulling back, it won't even be one document. It'll only be the first 4,000 tokens of the first document. So then I realized, okay, yeah, this chunk prefill is going to be giving you kind of more arbitrary stopping points throughout the document, and it makes more sense to not add noise, not add garbage, just only add stuff that you think is highly relevant. And then the ablation on the right is they said, hey, so in the middle is just vanilla rag, it's just the context. On the left is what if we threw away all those 20,000s? We could speed things up a lot if we just threw away the 20,000 and we only gave you the summary margin stuff. And so you can see that overall, um, the summaries are not perfect, and so they did do better by allowing the LM to truly see. And I think this is going to be more and more true the more you're doing like multi-hop, the more complex questions. Because for simple questions, you should be able to extract it. But that whole business of he's in John's living room and John's living room has a marble floor, maybe your extraction thing misses one of those because, it wasn't really sure or whatever. And then the LLM, it sort of sees like it got one of them that John's, living room is marbles. Like, okay, well, I'm really, really solid on that, but is he in John's living room or is he somewhere else? And it's maybe that helps it, boost its performance, but it can't rely on just solely those summaries. All right, to wrap up this paper, right, it's really intended for problems with long text. They cleverly designed a way to inexpensively extract these pieces of text. And my prediction is that we're going to see other papers figuring out other inexpensive ways to use the KV cache and to say, I've already got this information loaded up in chunk prefill. What else can I do with it? That's going to be slightly different from the way they're using it. And so those techniques, again, this is the maturity that we're seeing with LLMs. At first, it's like what you do. And then when you look at things like flash attention and when you look at writing in the margins, it's not about what you do because clearly writing in the margins is doing more work. It's the fact that they're able to do it in a way that the cost is much less than. Um, so right now I see a lot of optimizations coming out where it's really focusing not just on in total in a vacuum, what do you do, but you're running on a GPU with this memory architecture, with this pattern of reading things and doing matrix multiplies and whatever. And if you do this thing, that's going to be crazy expensive. And if you do this other thing, it's going to be really, really cheap. And so really looking at those kinds of trade-offs, I feel like that's a level of maturity that we're at. Um, and so again, they extract this relevant text, they append it there before the main prompt. And they got some pretty good results on things like hot pot question answering. There was also a part of the paper where they said, as you're generating these margins during chunk prefill, theoretically, not only can you take these summaries and save them to be inserted later, you could even send them back to the user so that they see them as they're coming through. And so that would sort of like shorten the latency. That would give the user a little bit more interactivity. And I didn't think too hard on those use cases, but they said like if the user saw like a really good summary, theoretically, they could hit like Control C and say, "Oh, I already got my answer. You don't have to. You can stop. You don't have to do any more work." Stuff like that. So I think there's other stuff that somebody could try to like iterate on and figure out, is there a way to build on this idea of like more interactivity?
Do they show references as to where this text is in these papers or database?
Uh,
In like these summaries, does it say like?
are you talking about the summaries this paper is generating or the documents that are coming back from the database?
Uh,
Yeah. So no, I don't think that they're able to easily describe where, because again, chunked prefill is doing its own thing of every X many tokens, right? It could start mid-word and end mid-word in just some arbitrary place. Um, so at least from what I recall in the paper, they say like, hey, here's what I've extracted. Dude is in John's living room, but not really what the greater text was that came from. there was actually a question in the Slack this morning. Um, what the heck do they call it? There's an Anthropic post about, I can't remember the name, context-based retrieval. Yeah, I can't remember the official name, but it's context retrieval, and that seems to like make a whole ton of sense because it's like if you have a document that's really, really long and it's getting broken into chunks as it goes into your vector database, it could be lost. Like, what the heck is this chunk? And I haven't had a chance to deep read it, but like if you said this chunk is from the 747 maintenance manual, chapter 3 about hydraulic fluids, section 1 about dealing with leaks, then when you're trying to do a vector retrieval, maybe like you have a much better, I think in the paper they had some other example where they're like, uh, uh, Bob was not a very good son. And it's like, whose son? Because we're like on the chapter all about George Washington's children, but it doesn't actually say George Washington anymore because we're just like in the middle of this and it's just talking about Bob and then it's talking about Mary and then it's talking about Joe and like, Mary was actually a really good kid, whatever. And like, whose kid? Yeah, so they're saying that like imagine that scenario then like if you actually know that this is the chapter about George Washington's children, then it just gives you a whole lot more context for this giant paragraph or section 3 pages talking about Bob being a brat or whatever. Was there something in the chat or
I've been linking stuff.
Oh, okay. Cool. All right. All right. So that's it. That's it for me. I have two links here. One is a paper. If you're more interested in chunk prefill and other ways of optimizing inference, there's this Sarathi technique where they actually talk about for different users mixing and matching prefill and decoding. And then Ryan actually found this great blog that goes and explains some of the things like chunk prefill and other things. And I haven't linked it. It's on the STML talks repo, but I haven't actually linked it. You'd have to like just know what folder it's in right now. But I'll go ahead and I'll get the link for that out. All right, thanks, guys. All right, I'll turn things over to you, Ryan.
Okay, I think we're good. I just wanted to make sure I didn't echo. Can you full screen it? Because it'll be sharing through you. Oh, sorry. Yeah. All right, cool. So I'll be talking about the Aurora foundation model. So this is a model that came out a few months ago. And so this is some work from Microsoft. So we've seen a lot of work on large language models. They train a big model and they say, guess the next word, and then it's amazing at text, and we have ChatGPT and all of this stuff. And so Aurora is kind of applying the same concepts to a different domain. So it's all about the atmospheric forecasting. So we've seen foundational models. They've been successful in text and video and drug discovery and all these other domains. And atmospheric forecasting is like a very powerful one because we have this wealth of data. We have many years of recordings, and we don't necessarily have labels specifically for all of the different types of things that we might want to do. So we can train a foundational model that knows a lot about the weather patterns, the temperature, the wind, the oxygen concentrations and rainfall and all of these other things. We have recordings of this. And so we can train a model just generically say every data set that we have, try to optimize to learn all of those things. And then when some new problem comes up, we can take this model and we can transfer it to that task. And we need much less data in order to actually get good performance out of it. So here's an overview of what the modeling and data will look like. So I'll try to go through all of this fast because we're a little bit over time, but we're plugging in a whole bunch of different data sets. So from all of these different sources, we have many different data sets and they come from different places and they might have different resolutions and they might have different temporal resolutions. So some of them might be looking at tiny little regions of land and others might be looking at much coarser grids. And then they also might be every 15 minutes, every 6 hours, every day. There's all kinds of different variations with that. And so with this, what they've done is they took all of these data sets, they aggregated them together, and then they said, train this model to do all of these different things. And so the heart of it is basically just simplified to the same thing that we do for text, where it's given a time step, guess the next time step, basically. So in large language model terms, it's I have these 8 words, guess the 9th word. So it's the same thing in this. We are given an image of whatever the current state of the world or some small portion of the world, and then guess what it's going to be in 15 minutes or 6 hours or a day or whatever the unit is. And so the architecture of this is set up so that they take in virtually any input, and then they have this 3D perceiver encoder that then puts it into a common 3D format that the unit then tries to do sort of the like time series next step piece of, and then they have a 3D perceiver decoder that will turn it back into whatever target they want. So the difficulty here, the reason that they have these extra encoder steps is these can be all kinds of different variables. So this might be the ozone concentration, and this might be the temperature of the air at various different altitudes and stuff like that. And so they need something that kind of merges all of these together into a common representation. And that's what this step is doing. So we have all of these different data sets. There's a bunch of different variables. We have spatial and temporal resolution going on. And then here's some information about all of the different data sets. So predicting a lot of different things. So we have the architecture is this perceiver encoder, and then the 3D transformer unit, and then the decoder that I was just describing. And so the shape of this input into the model is they have all kinds of different variables. So all of the different stuff that I've mentioned, but then they also can have it at different pressures. So the world is 3D, and then you have multiple different altitudes and pressures that you're measuring things. So you actually want to have, say, like, here's this variable at this pressure, and then there might be higher, higher, higher. So you can have 30 plus different elevations of a single variable. So you need some way to represent this is the same variable, just different elevations. So when we look at this data, we have the number of variables, the number of different pressures that we're looking at, the time steps. And so the way that they typically did this is they just had time step as the current time step and then the previous time step. So in some works, they're actually looking further back and looking many time steps behind. In this, they're only looking the previous 15 minutes or 6 hours or whatever the data set's unit is. And then they have the height and the width. So everything here is represented as images. So even certain things that might have a single value for everywhere, they just represent it as an image still so that it can get kind of blended in with everything else. So it might be a single value at a current time, but it's broadcast to this entire dimension. And then they also have certain static variables. So these are things that are just always passed in. And so you might go, why do you even pass it in if it's going to be constant? But it actually gives you some information about local regions. So you're telling if it's over land or over water, or this is a mountain, or there's other various different factors that you might look at. And so the way that this model is trained is it's actually just predicting the next time step. And that might be useful, but you might want to go further than that. So let's say your model is predicting the next 6 hours, but you want to predict the next 10 days, for example. So the way that you can do this is auto-regressively, like you do with the large language models, you just pass it back into the previous step. So you say, guess the next 6 hours, and then that next 6 hours becomes times zero again, and then you can pass that forward more and more times. And so they trained three different sizes of this model. They trained 113 million, 660 million, and 1.3 billion. And on that biggest model, it took them 32 A100s, 2.5 weeks. So it's a relatively big training job, but in terms of like large language models where they're using thousands of GPUs and training for a month, it's not actually that bad. So like a small research lab could theoretically do this. And so one of the big things that they point out is they're hoping that this model will be like exceeding accuracy in every metric, but at the same time, it's also just way more efficient than the physics systems that they compare against. So this IFS system that they compared against is considered the state of the art for some of this weather forecasting stuff. But in order to run it, to do a 10-day forecast for the next 10 days, it takes 65 minutes to run, and they need 352 36 core systems, so many, many systems. And then they compare that and they can create the next hour with a single A100 GPU. So they just run that for a few minutes and they get the same thing that you needed 352 powerful systems in order to create. So part of the angle is the accuracy, but then the other angle is like how efficient it is in comparison. So they did a whole bunch of really interesting stuff with the model details. I don't think I'll get into all of the details of that, but essentially it's figuring out smart ways in order to handle that you're getting these variables that are actually at different altitudes. So you need some way to represent this is the same variable at different altitudes, and here's how we understand the spatial element, and here's how we understand the temporal element. There's many different axes that you're looking across, and so they've tried to be really clever on all of these in order to make it as efficient as possible. So one of the important pieces about this was the data variety. So one of the things that they did some studies on was just like, we have this good ERA5 data set. How do we do if we only train against this and then evaluate its performance at that ERA5 task? And then at the same time, what happens if we add in other data sets for completely unrelated things? It's not even the same weather forecasting task. But what they found is that adding those other data sets at different resolutions, at different temporal resolutions, they still get some benefit out of it. So what they've done here on these graphs is they show the blue line is always at 100%. That's what happens when they only train on the ERA5 data set. And then they show adding in other data sets, they get better performance when they pre-train on those tasks as well. So you can see when this C4 is saying they added in all 4 data sets, and then instead of getting 100%, like 100% is their baseline error, and then they can get down to 96%. So they got 4% less error essentially. So they also did some studies on the model scaling. So they trained those models at 3 different sizes. And what we've seen with large language models is that bigger model just is better, and you want a bigger model in reference to your data. And so they did the same thing here, and they said, let's train for the same amount of GPU hours, and they were finding kind of similar scaling laws, where it's like, if we make this model better for the same amount of compute, we can get a better resulting validation loss at these tasks. So they figured out what the scaling law is. And one of the key things that they found here is that the biggest slowdown in a lot of this stuff is the data loading, because when you're pulling in this information about the entire Earth and you're saying like one little grid is 2 gigabytes, and then I'm going to train on that one data point, it's very, very slow to load the data. So one of the things you'll notice in these graphs is for these are all equivalent number of GPU hours. You would think that a model that is 10 times bigger would probably have about 10 times less tokens that it consumed. but in reality, it's probably over 50% because a lot of their time was actually on data loading. It wasn't actually on model processing. So you make your model 10 times bigger and it's not 10 times slower. It's only half as slow because most of the difficulties in the data loading, not actually in the model processing. So they pre-trained this model. Now they have a 1.3 billion foundational model, and then they wanted to see how good is it at all of these different tasks. And so the first one that they looked at is this CAMS task, Copernicus Atmosphere Monitoring Service. And this does several different things. It can do forecast analysis, reanalysis. And before I was talking about that IFS system that was so painfully slow, this CAM system is built on top of that and even slower than that because it's trying to integrate additional additional factors that just come from like human emissions. So they're talking about these anthropogenic emissions. So all of the stuff that humans burn a forest or run a factory or do whatever, we have some information about the information of what they're shooting into the air, essentially. And so this system, because it relies on a lot of other data sources, is even 10 times slower than the IFS system. And so what they found is that this model, even though it doesn't have those additional sources, beats it at 74% of the targets. So it's really powerful that it doesn't need to know all of the stuff of what we're shooting into the air and how we're interacting with the atmosphere. It's just so much better at understanding the movements that it doesn't need to know the surface level what's happening. And so this visualization here is showing what Aurora was given as input, and then 6 hours later, or 12 hours later, this is what its prediction is, and it's very, very similar to what the CAMS analysis is. So this is the like label essentially. And then this is one of the graphs looking at performance. So they have all of these different variables that the models are predicting. And then you can see on the left-hand side, we're going from left to right in terms of lead time. So this is saying predict out the next hour, 2 hours, or maybe days. So this is predicting out the next 12 hours, 24 hours, etc. So you're going 12 hours out each of those squares. And you can see that the IFS CAM system is more accurate at the very, very near term for certain things, for certain pressure levels. But as you go further out into the horizon, it's better at predicting a lot of these variables. And so the one that is particularly difficult for it to predict is this ozone prediction, and that's the one that the anthropogenic emissions has a big factor on that. So it's more difficult for it to predict that because it doesn't have the extra inputs that the other one has. And then this graph down here is showing the relative error for all of the different pressure levels and all of the different variables that they're predicting. And so you can see it beats it by a significant margin on the majority of the tasks, especially 3 days out. So it's strong at 3 days. So another one of the tasks that they're looking at is just weather forecasting. So one of the things that they were pointing out is that we have a lot of data at one lower resolution that goes all the way back to 1950, but we only have this new higher resolution data from 2016 onward. And so one of the things they were measuring is what happens when we train on that lower resolution data from all the way back to 1950 and then try to transfer it to the higher resolution data, because the higher resolution data is a relatively small time window. It doesn't have enough context to be very, very strong. And so what they found is that it's significantly better when you do that transfer. So it can handle many different resolutions. And so this one is saying each grid tile is 11 kilometers, and this one is saying that each grid tile is 28 kilometers, basically. So you can see there's a jump in resolution, and in turn, this model ends up being better because it's much more fine-grained. And this is a small graph, but basically the outcome is just that it's better across every every time step, all lead times, all factors when you do that transfer. So here's one of the other graphs they showed was basically that doing this pre-training on many different data sets and across a further history, it's able to handle these extreme cases much better. So what they're trying to show here is that there was this hurricane and all of the other forecasting systems greatly underestimate the maximum wind speed at this certain point because it hasn't seen enough of these outlier events. And so saying going all the way back to 1950 and many different data sets, it's able to say, okay, I've actually seen this a few times across the years, whereas all of these other systems say, I only know some basic physics or I only know the past few years, they don't have enough examples to represent these kinds of predictions. So this Aurora 0.1 is able to get this kind of sharp peak that they expect for when this hurricane came through. So the last bit that I'll talk about is this rollout fine tuning, which I thought was kind of interesting. So like I mentioned before, if you are making these predictions, it's set at some fixed prediction interval. So it's only guessing 15 minutes ahead at a time, for example. And what you can do is pass that prediction back to the original model and then have that try to autoregressively go to the future. But if the model was always trained on the high resolution, high fidelity results, like from the true history, then the predictions might vary from what was passed to the model before. So they did this replay buffer thing where they basically said, do these predictions and then create a data set of the future predictions and then pass that back as input and train that to try and predict the future steps again. So you're continuously building this history and updating it and trying to say, okay, my predictions are now given this old prediction to guess the future steps. And so in this way, they can make it so that the model has actually seen and ingested predictions before rather than just ground truth. Because if it was only shown ground truth, then when it was trying to make predictions in the future, it would probably just stray from the path and then not know what to do. And so this is a way to make it more robust. Yeah.
So then basically without the replay buffer, you just have that problem where the errors compound. And so this is the way to try to make it a little bit smarter about that so that they don't just pile up.
Yeah. Yeah. So if you have T0, it predicts T1, and then that's probably varied from the truth. And so if it's only good at predicting T0s, it's never good at ingesting T1s. So the T1 is kind of learning how to make the corrections of the previous errors, or at least attempting to put it back on the right track. Yeah. All right. And that's all I have. Any questions?
It's supported with the recursive forecasting, right? For the initial 15 minutes, it's forecasting, and then take that as the input, and then forecasting the rest, and say it goes to 6 hours. And in that, we can integrate the parameter errors for each step, right?
Yeah. Yeah. So it's passing back into itself. Yeah. Yeah.
All right. So that concludes our presentations for today. Thanks everyone for joining, and yeah, thanks for your patience with some of my technical difficulties. Join us on Slack if you have any other discussions between now and otherwise. We hope to see you first Saturday of November. Thanks, everyone.